If you need to direct a Boda Boda rider to a specific house in a busy part of Kampala, you rely on two pieces of information: how far to travel down the main road and how far to turn down the side street. To pinpoint an exact location on a mathematical map, we use a similar system called the rectangular Cartesian coordinate system. It is formed by crossing a flat number line with a standing number line. The flat number line running left to right is the x-axis. The standing number line running top to bottom is the y-axis. The exact center where they cross at 0 is the origin. To plot a location, you follow the golden rule of coordinates. Walk along the corridor of the x-axis before you climb the stairs of the y-axis. A surveyor mapping a triangular plot of land in Wakiso uses this mathematical system to place boundary flags. To place the first flag at coordinates -4, 2, we apply the golden mole. Starting at the origin, we walk 4 units to the left into negative numbers on the x-axis, then climb 2 units up the y-axis. The second flag is at 3, 2. We reset to the origin, walk 3 units right into positive numbers, and climb 2 units up to match the height of the first flag. Now for the third flag at 3, -5. Take a moment to mentally plot this point on the grid. Once it is placed, what is the exact length of the vertical side connecting it to the second flag? Starting from 0, we move 3 units right, then climb down 5 units into negative territory. Connecting these points forms a vertical side starting at +2 and ending at -5. That covers a total distance of exactly 7 units. Navigating accurately across both positive and negative coordinates allows us to map geometric shapes and calculate exact distances anywhere within a defined space. We also use the Cartesian plane to map relationships between two different variables, known as bivariate data, like comparing the heights and ages of 5 students. This table displays our raw bivariate data. The students' ages range narrowly between 12 and 15 years, while their heights stretch across a much wider range, from 110 to 160 centimeters. If you put height on the y-axis and count up from 0 by single centimeters, you will need a piece of graph paper over a meter tall just to fit the highest data point. Instead, we compress the empty space by breaking the y-axis. We start our baseline at 100 centimeters and jump upward in mathematically equal increments of 10. We plot each student's coordinates onto this scaled scatter graph to clearly reveal the relationship between their age and height. Maintaining consistent axis scales is mandatory. If the distance between your grid lines changes, the visual comparison of the data becomes distorted and unusable. Once the scatter graph is properly built, we can identify specific values for each student by reading the spatial layout directly. This chart shows the highest plotted point sitting near the top right corner. Tracing backward, we drop a line down to 15 on the x-axis and across to 160 on the y-axis. The position alone tells us this point represents Faith, the oldest and tallest student. Every reliable coordinate map follows 3 strict rules. Start at the origin, walk the horizontal x-axis before climbing the vertical y-axis, and ensure your axis scales are mathematically equal. By mastering these rules, you are learning the exact mathematical grid that coordinates GPS satellites, anchors architectural designs, and builds digital worlds.